My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about semiconductors. What's meant by a semiconductor? What are the factors affecting conductivity of a semiconductor? Types of semiconductor, intrinsic, extrinsic, and extrinsic semiconductors are classified into two types, N-type and P-type. So let's get started. Semiconductors. First of all, what's meant by a semiconductor? A semiconductor is a material which has an electrical resistance in between. It is a rank in between those of insulators and conductors. So it is a rank in between insulators and conductors. Let me say it again. A semiconductor is a material which has an electrical resistance in between those of insulators and conductors. The electrical conductivity of a semiconductor depends on. So talking about the factors affecting conductivity of a semiconductor. And of course, there are the same factors affecting electrical resistivity. Okay? What about these factors? The first factor is the temperature. Okay. Conductivity of a semiconductor. A semiconductor increases with the rise in temperature. And the second factor affecting conductivity or affecting resistivity is the presence of impurities. Presence of certain impurities. Okay. As a matter of fact, when some certain impurities are added in controlled amounts to a semiconductor, the conductivity of the semiconductor increases. Okay, now we can define a semiconductor. What about it? It is a material that is characterized by the fact that its electrical resistance decreases with the rise in temperature and presence of certain impurities. Note, a semiconductor has some electrons in its lattice that are more tightly held than in a metal, but less tightly held than in a non-metal. At 0 Kelvin, this is very important. At absolute zero, a semiconductor has no free electrons to act as charge carriers. So it's considered a perfect insulator at this temperature. At 0 Kelvin, at the absolute zero, a semiconductor has no free electrons to act as charge carriers. So it is a perfect insulator at this temperature, at 0 Kelvin. As a matter of fact, all bonds in the crystal are, yes, unbroken. They are intact. At room temperature, few electrons are freed at any room temperature other than 0 Kelvin. Yes, a few electrons are freed by thermal excitation, and hence a slight conduction of electricity can occur. Raising the temperature of a semiconductor causes some valence electrons to become free. and thus the ability of a semiconductor to conduct electricity increases with temperature, with rise in temperature. And now talking about pure semiconductors. We call them intrinsic semiconductors. So intrinsic semiconductors, okay, are pure semiconductors. Intrinsic semiconductors are pure elements such as silicon and germanium. Mainly we use silicon. Okay? Silicon and germanium are tetravalent. They've got 4 electrons in the outermost energy level. They are tetravalent. They have 4 electrons in their outermost energy level. Okay, these electrons are called valence electrons. Therefore, each silicon atom or germanium atom shares 4 electrons with the 4 neighboring atoms, so that the outer shell contains, when sharing, the outer shell contains 8 electrons. Thus, in the silicon and or germanium crystal, each atom is bound to 4 neighboring atoms with 4 single covalent bonds. At 0 Kelvin, all the valence electrons are firmly bound to the nucleus of their particular atom. So the crystal is a perfect insulator at 0 Kelvin. But at room temperature, at any temperature other than 0 Kelvin, the energy of a valence electron may become greater than the binding energy of the nucleus. The covalent bond is then broken and an electron is set free. Electron is freed. Such an electron leaves behind a vacancy in the broken bond. We call it, the vacancy is called positive hole. This vacancy is called a positive hole. A hole is an empty energy level in the valence bond. We don't call a silicon atom which loses an electron from its bond an ion. Why? Because this atom will capture a free electron or an electron from another bond to fill its vacancy. This captured electron, however, leaves behind a hole on the previous atom. Thus, as in a game of musical chairs, the negatively charged free electrons move in one direction and positively charged holes move in the other. So they have 4 electrons. Talking about silicon or germanium, they have 4 electrons in the outermost energy level. And they share these 4 electrons with 4 neighboring atoms so as to obtain 8 electrons. Okay? So once again, they've got 4 electrons in the outermost energy level. They are called valence electrons. And there is something here we should add. As I said, at any temperature other than 0 Kelvin, yes, thermal excitation or thermal agitation occurs, and an electron is set free, leaving behind a hole. We call it positive hole. Then electron from a neighboring atom fills this vacancy, and a hole appears in the neighboring atom. Okay, it is shown in front of you. Now, one electron is set free, then electron from Y is moved to fill the vacancy. We've got important hints here. First of all, the number of free electrons equals the number of holes, number of positive holes in a pure semiconductor. So, number of free electrons, small n, equals number of positive holes, which is P, and each one of them is equal to Ni, or could be denoted by Ni in intrinsic. At any given temperature, other than 0 Kelvin, a state of thermal equilibrium is reached. We've got an equilibrium between what? A state of thermal equilibrium is reached where the number of bonds that break equals the number of bonds that recombine, so that a fixed number of free electrons and free positive holes is there at any given temperature. But this number will be increased when increasing the temperature, we're raising the temperature. So at any temperature we've got an equilibrium state, thermal equilibrium state between the bonds that break and the bonds that recombine. Okay, such that we've got a fixed number of free electrons and positive holes. As the temperature increases, the number of free electrons and holes increases. That is to say, the number of bonds that break increases and a new thermal equilibrium state is reached. And now talking about the second type of semiconductors, it is, yes, extrinsic semiconductors or doped semiconductors. They are the semiconductors in which we add certain impurities with the controlled amounts. So talking about doped semiconductors. By doping a semiconductor with a tiny amount of impurity, okay, causes a considerable increase in the number of charge carriers. Doping increases conductivity by adding either electrons or holes. And now talking about N-type semiconductors. So extrinsic semiconductors, yes, are classified into two types, N-type semiconductor and P-type. And now we are talking about N-type semiconductor. As a matter of fact, the addition of a pentavalent element, so in N-type semiconductor, a pentavalent element such as phosphorus, antimony, arsenic, okay, will increase the number of free electrons. Will increase the number of free electrons. Antimony, for example, have 5 electrons in their outermost energy level, and they want to reach 8. They've got 5. Okay, when an atom of antimony is added to a silicon crystal, the atom settles in the lattice, in a lattice site, with 4 of its electrons shared with neighboring silicon atoms, 4 neighboring silicon atoms. In this way, we've got, yes, an electron which is not, yes, bound to any particular atom, it is free. The 5th electron is not needed in bonding, and so it becomes free to move through the crystal. So by adding antimony, we increase the number of, yes, free electrons. In front of you, it is shown. Okay. Antimony has 5 electrons in the outermost energy level. To reach 8, 4 of these electrons are shared with the electrons of 4 neighboring silicon atoms, and the 5th is free. So an enormous increase in the free electrons will occur. Okay, so we've got an excess electron, free one. Free means it's not in a bonding. Since an impurity atom may provide one free electron, an enormous increase occurs in the number of free electrons. The impure semiconductor is called N-type semiconductor, where N represents the negative charge on the electron. Thus, the majority charge carriers in this case will be, free electrons. But there is something very important to mention here. The crystal is still, neutral. It is N-typed. The name is, it is named after the majority charge carriers. Charge of the majority charge carriers is the charge of electrons, negative charge. So we call it N-type semiconductor, but it is neutral. In the N-type semiconductor, there are free electrons. Okay, positive holes are also present in the N-type semiconductor, but positive holes are the minority charge carriers. Majority is the free electrons. Positive holes are thermally generated, and since they are relatively few, they are called the minority charge carriers. In the N-type semiconductor, the majority charge carriers are free electrons, minority are positive holes. It is shown in front of you. We've got free electrons, and they are majority charge carriers. Majority comes from impurities, but minority is positive holes, and they are thermally generated. Okay? Important note here. Adding dopant atoms, impurity atoms, does not add any netted charge. This is very important piece of information. Adding impurity atoms does not add any netted charge to the semiconductor. It means it remains, neutral. The semiconductor is still neutral, as if there are free electrons, then there are same number of positively charged holes and ions. That is to say, the crystal as a whole didn't lose or gain any electrons, so it is still neutral. Also, adding N-type impurities decreases the concentration, the number of positive holes. Since impurity atoms give free electrons, they are called donors. At thermal equilibrium, the sum of positive charges equals the sum of negative charges. Okay, so why it is still neutral? Because the number of free electrons, which are negatively charged, equals, P positive holes and the concentration of the positive ions, where Nd positive is the positive impurity concentration and is the free electron density. P is the positive density or positive hole density. Density means number here. In this type of semiconductors, in N-type, N is much greater than P. Free electrons are the majority, P positive holes minority. So number of free electrons is much greater than the number of positive holes. That is why it is called N-type material. are now talking about p-type semiconductor. What about p-type, the other, yes, type of extrinsic semiconductor? P-type semiconductors are made by adding atoms which are trivalent. Trivalent means they've got three electrons, three valence electrons in the outermost energy level. So p-type semiconductors are made by adding atoms which are trivalent to a pure silicon crystal. Okay, in front of you, the impurity atoms are boron. Okay, each impurity atom has three electrons in the outermost, and they want to reach 8. So what happens? They'll create a positive hole here. The impurity atom may be, as I said, boron or gallium, aluminium, or indium. They've got 3 electrons in the outermost. Okay. Each boron atom has only 3 valence electrons. If a boron atom replaces a silicon atom, one binding electron is missing. One binding electron is missing. So, that is, the boron atom creates a hole here. Okay? Thus, each boron atom attracts an electron from a neighboring atom to complete the 4 valence bonds, so it forms a positive hole in the neighboring atom. And this way, an enormous increase occurs in the number of positive holes. So the majority charge carriers in this type will be positive holes. And this will be at the expense of the number of free electrons. Free electrons, okay, are thermally generated, and they'll be minority charge carrier. So in this way, an enormous increase occurs in the number of positive holes. Okay. As I said, we've got positive holes and free electrons. Free electrons, and they are minority charge carriers, and they are thermally generated. Positive holes are generated because of the presence of impurity atoms. Okay, each atom attracts, yes, an electron from a neighboring atom, thus creating a positive hole. Thus, the majority charge carriers, as I said, are positive holes. Minority are free electrons. Minority are thermally generated. The impurity atoms are called acceptors because each atom accepts an electron, attracts an electron. Note, when the impurity atom detaches an electron from a neighboring atom, the impurity atom becomes a negative ion. So at thermal equilibrium, we can say P is equal to Na negative plus N, small n. Okay, where Na negative is the negative impurity concentration. In this case, P, number of positive holes, is much greater than the number of small n, number of free electrons. So the crystal is called p-type crystal or p-type material. Important note here, adding dopant atoms, impurity atoms, does not add any netted charge. This is very important piece of information. Adding impurity atoms does not add any netted charge to the semiconductor. It means it remains, yes, neutral. The semiconductor is still neutral, as if there are free electrons, then there are same number of positively charged holes and ions. That is to say, the crystal as a whole didn't lose or gain any electrons, so it is still neutral.